Hello everyone, welcome back to Applied Thermodynamics subject. Today we are going to see some examples related to the first chapter, related to the different types of gas power cycles. So the first example which we have here is for a diesel cycle. This example is from the textbook, the Sengel textbook actually, and the number of example is example number 946, and it is from 8th edition of this textbook. So let's see what is the question. We have an air standard diesel cycle. This cycle has a compression ratio of 16 and a cutoff ratio of 2. At the beginning of the compression process, air is at 95 kilopascal and its temperature is 27 degrees Celsius. Accounting for, this is also very important, accounting for the variation of the specific heats with temperature. Now we need to determine A, the temperature after heat addition process, B, the thermal efficiency of this diesel cycle, and finally in part C, we need to determine the mean effective pressure of this cycle. Uh, if you remember, uh, I in if you remember, I told you that uh, uh, you need to know the cycle, the diesel cycle in TS and PV diagram, and it is very important here to solve such a example actually. Moreover, for to answer each example in thermodynamics especially, we need to have some relevant assumptions. Here it is mentioned that, in the question it is mentioned we have a standard diesel cycle. So the first assumption which we can have is their standard assumptions are applicable. This is mentioned in question instruction, and also we can have these assumptions. Moreover, assumption number two, the kinetic and potential energy changes are negligible. And finally, air is an ideal gas with variable specific heats, which was also given in the questioning instruction. The next step to answer to this question actually is to draw this PV graph for the diesel cycle. This is a PV graph for diesel cycle. Here we have isentropic process, compression isentropic process, constant pressure expansion, and a isentropic expansion process, and finally from state 4 to state 1 a constant volume process or heat rejection process actually. So by this we know how is the cycle for our example here. The other properties, which the properties actually, or thermodynamics properties, which are important here for this example, is based on what we mentioned here in the assumptions. Air here is ideal gas. So for the gas as ideal, for the air as ideal gas, R or gas constant is equal to 0.287 kilojoule per kilogram Kelvin. And also, as I mentioned, based on these assumptions, the properties of air can be found in the table A70. Now we have our assumption. We have the properties which are required for our working fluid. Now let's see how we can use, the knowledge which we have here, the information which we have from question instruction to find the answer for these three parts. In part A, it is mentioned that temperature after heat addition process. It means, if you just look at the graph, we need to find temperature for this state or T3. So in part A, we need to find the temperature after heat addition process, or T3. But how is the procedure? How is the procedure to find this temperature? If you remember, and also we had in the first example in this chapter for Otto cycle, or even for any other type of the cycle, we are always interested to find properties for each state in the cycle. But usually we have only information about some specific parts, specific states in the cycle. Here, the information which is given actually is, let me just read again from the question. We have the compression ratio. If you remember, compression ratio means how much is the Vmax divided by Vmin. So compression ratio is 16. Cutoff ratio is cutoff ratio of this cycle is 2, and at the beginning of the compression process, air is 95 kilopascal and its temperature is 27 degrees Celsius. So here at the beginning of the compression process. So let's see where is the compression process in our graph. Here from state 1 to state 2 we have compression. So what we have here at the beginning of the compression process means we have P1 and we have T1. P1 and T1 actually are given 27 degrees Celsius. P1 is 95 kilopascal. Let me just check it again. Yep, and compression ratio is 16. Compression ratio, you know, we show that by R is 16, and the cutoff ratio, which we show by RC, is equal to 2 actually, which you can see here is given. So we have this information, our assumptions, the graph, and properties. Now let's see how we can use this information to find T3. First of all, we have information for state 1, the properties for state 1. By the information which we have for state 1 and also we know what is the process from state 1 to state 2, we can find properties, thermodynamic properties for state 2. Then from that, we can find properties for state 3 by the properties which we have for state 2 and also the process which we have from state 2 to state 3. So first, let's see how we can find properties for state 2. For state 2, we have an isentropic process here. So process from state 1 to state 2 is isentropic compression. This is the information which we have for this process. Moreover, we have temperature for state 1. Temperature here is 27 degrees Celsius plus 273 will give us the temperature based on Kelvin unit. Temperature, or T1, is 300 Kelvin. So to find the thermodynamics properties for this temperature, we can refer to the table A17. This table temperature is 300 Kelvin, and we can come to this table. You know, this is table A17, the ideal gas properties of air. The temperature is 300 Kelvin. So the thermodynamic properties for the air as the ideal gas in this temperature can be read from this table. So we can find properties like internal energy, or U1, and also relative specific volume for state 1 from table A17 directly. And fortunately, we don't need to go interpolation to find this property. So we can find directly U1 and VR1 as the internal energy and also relative specific volume for air in state 1. Now we have these properties for state 1, and we know the process from state 1 to state 2 is isentropic compression. For isentropic compression, actually, we have also this equation. This equation is valid only for isentropic processes, which based on this equation, the relative specific volume, actually this equation is in this form actually, and this equation is valid for a process, for an isentropic process, which 1 and 2 shows the two states which this process go through those states actually. So here this process is between the state 1 and the state 2, so we can write this equation because we have isentropic process. This is important. Isentropic process, this equation can be written. VR2 equal to V2 divided by V1 times VR1. So here we have VR1 from a table. Then how we can find V2 and V1 to calculate VR2 or the thermodynamic property for state 2. How we can find that? If you notice here, V2 and V1, V1 is here and V2 is here. And also if you notice here, compression ratio which we have here is V1, the maximum maximum volume divided by the minimum volume of the cylinder or the system actually. So V1 divided by V2. What we have here is V2 divided by V1. So it means this is 1 divided by R actually. V2 divided by V1 is 1 divided by R. If you see this, compare this equation, R equal to V1 divided by V2, it will give us this V2 divided by V1 will be equal to 1 divided by R. Okay, so we have R, the compression ratio, we have VR1 from previous step, so simply we can find VR2, 1 divided by 16 times 621.2 as a relative specific volume. And if you notice here, relative specific volume is dimensionless, and actually the role of this relative specific volume is a property to find the other thermodynamics properties for different substances from table easily. It will help us to find them actually, the other properties, if you remember from thermodynamics. So 1 divided by 16 times this 621.2 will give us this amount of the relative specific volume for state 2. So we found VR2 for state 2. Now we have a thermodynamic property for state 2. We need to go to the table A17 and find the other thermodynamics properties for this state. To do that, okay, how much is this VR2? 38.8. So let's see. So 38.8 is VR2. Let's see where is in our table A17. VR2 38.8. So let's see here. You can see we are, when temperature is low, VR is high. As much as temperature is increased, the VR also is reducing, and you can see here we are 38, and okay, here we have 39 for VR, and here is 36. It means VR, which we have here, is between these two. So to find temperature and all the other properties for this state, we need to have to do interpolation. How we can do that? First of all, let's see what are the properties which we are looking for. The first property which we are, uh, all of these properties actually are important inside this box actually. And the property which we can find here actually, we can find temperature or T2, we can find H2, we can find PR2, we can find even U2. But how we can find that? By interpolation. How is this interpolation process? I will, because we will have interpolation in rest of these examples as well. Here we will do interpolation to find this property. The procedure actually is same. So here I will do the interpolation to find these properties for the state 2 in this example. Later on, you can just refer the procedure which I tell you here to do interpolation also for the other examples, or to find the thermodynamic properties for different states. So let's see how we can do these in the interpolation. Okay, now let's see how we can find temperature and enthalpy for state 2 in this cycle, this diesel cycle, by interpolation from this table A17, which is table for thermodynamics properties, or properties of air as an ideal gas actually. What we have here is one thermodynamic property, which is VR, or uh, relative specific volume. VR which we have actually is 38.825, and this is a dimensionless property. And actually it is a property which we can use to find the other thermodynamic properties usually. So let's see what are where we can find estimation of the VR or temperature in the table. VR which we have here is 38. So let's see, we are here. You can temperature. You can see here temperature is increasing. VR is reducing. We are start from 1,700 for temperature. When the temperature is 200 Kelvin, and it is reducing here. If we follow just, we are, here it is 78 until we reach 39, and here 36, which is less than we are which we have. So here is 36 and here is 39. So the the VR, or relative specific one, which we have is in between these two values. So the other thermodynamic properties also will be between the thermodynamic properties for these two different states actually. So now let's see how we can do interpolation here. First, we need to bring out this information from table. Imagine we first want we are interested to find T2. So we need to have T, and we are actually, so we need to make this table. For temperature, the temperature which we have here, actually we need this information from table. So we are which we have is 39.12. Our we are which is 38.825, and here 36.61. How about temperature? The temperature, its unit is Kelvin. When we are is 39.12, temperature is 860. And when we are is 38, we don't know how much is temperature. It is T2. And when we are is 36.61, T, or temperature, will be 860. 80. So first we need to come out with this table. So we extract the information from this table A20, the relevant information. Now let's see how we can use this information. Generally, to do interpolation, actually, we can have this general procedure. We need to make a table of x and y's, x1, x2, x3, for example, y1, y2, y3. Then here, to write this equation, actually, to for example, imagine in this table which we have created here, x2 is our unknown. Then we can, or even we don't know what is unknown here, we can write the equation like this, x2, the medium minus a minimum, actually, x2 minus x1 divided the maximum minus minimum, x3 minus x1 equal to y2 minus y1 and y3 minus y1. Then this equation actually can be used to find any other property. Okay, then this equation can be used to find any other, any one of the variable in this equation. For example, imagine we are interested to find x2. Then x2 will be equal to x3 minus x1 times y2 minus y1 divided by y3 minus y1 plus x1. So by this we can find the value for x2, which is our unknown, from the table which we have here. X2 is unknown, so we need first to come out with this equation, and finally we can find by restriction of the this equation, we can find x2 as the unknown in our equation. With the similar procedure, we can find T2 here in our table. If you notice here, we have a similar, table. If you notice, we have x1. X1 is 860. X2 is T2. X3 is 880, and so on. So with similar procedure, actually, we can write the equation to find the T2. Okay, here is our data. Now we can use the interpolation procedure to find T2. Here, if we write that equation simply, we can write T2 minus 860 divided by 880 minus 860 equal to 38.825 minus 39.12 divided by 36.61 minus 39.12 12, actually 39.12. So now if you restructure this equation, we can write T2 is equal to 880 minus 860 times this equation, 38 minus 39.12 divided by 36.61, 39.12. All of these need to be added to 860. Then if we solve this equation, actually, we can find T2 as our unknown in this equation, which T2 actually will be equal to 862.35, or roughly it will be equal to 862.4 Kelvin. And this is what we found for temperature at state 2. To check if our interpolation is okay or not, we need to compare the temperature which we have with the other two temperature. As you can see here, T2 need to be between 860 and 880. If we check here, the T2 which we have here is 862. So 862 as T2 actually or is between 880 and 860. So here by this method also we can check if the our interpolation is okay, if the temperature or the any other property which we found is okay or not. Let's see how we can find the other important property for this part of the example, which is enthalpy. With same procedure, uh, interpolation procedure, we can find enthalpy for this state as well. Okay, now again, here we are going to calculate another thermodynamic property. We are going to uh, do an interpolation to find the H or enthalpy for state 2. What we have here again is we are, which is equal to 38.825. So this is VR, which we have. Again, with same procedure, we need to come to the table. We find the approximate place or estimation of the place of the VR in the table is between these two and these two VR. Then we can find enthalpy for these two states. Enthalpy here, so this is the enthalpies, and this is the relative specific volume. Again, we need to create the table like this. VR and H which uh, we have here is 888.27. H2 we don't have, and 910.56. How about we are 39.12? The we are which we have 38.8025 and 36.61. Simply we can extract this information from the table. Now again with same procedure we need to write the equation. To write this equation, you know, this to this and this to this. So first H2 minus 888.27 divided by 910.56 minus 888.27. This is equal to, again, with same procedure, first this, next this. So 38.825 minus 39.12 divided by 36.61 minus 39.12. So we have here this equation. Now let's see how we can find the rest of this. Actually is just a simple calculation, just elementary things, and actually school things. Actually, you can simply find the answer for this equation. H2 will be equal to 910.56 minus 888.27 times 38.825 minus 39.12 divided by 36.6, 39.12 plus 888.27. So by this, if you solve this actually, H2 will be equal to, read from my text, 890.89 or 890.9. What about the unit? Unit, the unit which you find for H actually is unit you have in the table, which also I need to write here, kilojoule per kilogram. So the H2 also which you find here is kilojoule per kilogram. So by this you can also find H2. Again, to check that you need to compare the H which you find, which you calculate here with the enthalpies which you have here. Here we have 880 and 910. What 888 and 910? What we have actually is between those two, 880, 890 and 910. This is what we found, which is actually between these two, and it satisfies also the checking method for the interpolation. So simply you can see how you can use interpolation to find thermodynamic property from this table A17. Actually, for this chapter 2, you only need to use this table A17 to do interpolation, because as I said, in the generally for the gas power cycle, we have a standard assumption, and usually the working fluid is A. So you need to just to know how do interpolation for this table A17. So let's go to the example and continue the answer for the question. Okay, you have seen how you can find the T2 and H2 as temperature and enthalpy for state 2 by interpolation from table A17. But the question, the part A of the question is how much is the temperature at the end of the heat addition, or actually the heat addition expansion process. So we need to find temperature for state 3. How we can find that? From again with similar procedure, actually with the information which we have for state 2, and which with the information which we have for the process from state 2 to state 3, we can find the properties for state 3. The process from state 2 to state 3 is a constant heat addition process, and based on the ideal gas law, actually, because here based on our assumption we have the air in this engine or in this cycle actually is the ideal gas, so we can write ideal gas law, which for this process from state 2 to state 3, we can write P3V3 divided by T3 is equal to P2V2 divided by uh, T2. If we write this equation actually, and by the information that P is constant during this process, the P will cross out from both sides of this equation, then V3 divided by T3 will be equal to V2 divided by T2. If we restructure this equation, we can write based on the only T and V as the temperature at the state 2, 3, and temperature at the state 2, specific volume or even volume at the state 3, and volume at the state 2. So T3 will be equal to V3 divided by V2 times T2. But if you notice here, V3 divided by V2, V3 divided by V2, V3 divided by V2, if you notice, is the cutoff ratio. If you remember about the cutoff ratio, we mentioned that the cutoff ratio is the uh, volume of the cylinder at the end of the constant pressure expansion process, actually, to the volume at the beginning of the constant pressure expansion process. So we can write T3 is equal to V3 divided by V2 times T2, and here instead of V3 divided by V2, we can write cutoff ratio. And based on the questioning instruction, cutoff ratio is equal to 2. So T3 will be equal to 2 T2, which T is the temperature of state 2, which we have calculated already. And also we have cutoff ratio as well. So 2 times 862.4 Kelvin will give us the temperature for state 3. T3 will be equal to 1724.8 Kelvin. So we found the temperature for state 3. Now to find the other thermodynamic property for this state, we can again, here we have a thermodynamic property, T3, T or temperature actually for state 3. Then we can go to table A17, use this table and find enthalpy and relative specific volume for this state, H3 and VR3, which uh, you need to do interpolation to find this enthalpy and specific volume for this state. If you do that interpolation, you need to do two interpolation actually to find H and VR. H3 will be 1910.6 kilojoule per kilogram, and VR3 will be equal to 4.546. I'm not going to go through the interpolation because the procedure is same. You need only to find the or locate the temperature in the table, then find the enthalpy and we are by the interpolation procedure, which you have already seen for previous step. So this is the answer for part A, temperature or T3 at the end of the heat addition process. Now in part B, we need to find thermal efficiency of the cycle. How we can find that? If you remember, we have this equation for thermal efficiency, because here is mentioned that the thermal efficiency which we need to calculate or find should be based on the change in the specific heat or constant pressure specific heat with the temperature, or in other words, we cannot assume that a specific heat is constant or specific, or we cannot use cold air standard assumption. So to calculate thermal efficiency, we need to use general equation to find thermal efficiency for this cycle, or thermal efficiency for the diesel cycle will be equal to 1 minus Q out divided by Q in. So we need to find Q out and Q in based on the information which we have here. Q out and Q in is not given for the cycle, but we can calculate that. First of all, Q in, if you notice in the cycle, Q in is in the process, constant pressure process here from state 2 to state 3. And if you notice here, we have the reason for the change in the energy of the working fluid or system here in this process is only due to this Q in. And if you notice, we have written already in our assumption that we can ignore kinetic and potential energy changes during this cycle. You can see here why the assumptions are important, because this equation to find Q in, the general form of this equation is like this, delta Q plus delta W is equal to delta E actually, and delta E is equal to delta K plus delta P plus delta U. Here we ignore these two, then we can write this equation, and we don't have W during this constant pressure, so we have Q in equal to the change in the enthalpy of the system here, because we have a constant pressure process, so the change in the energy of the system will be equal to change in the enthalpy of the system during that process. Q in equal to H3 minus H2. I have already discussed about this equation in the proof of the thermal efficiency of different type of the cycles up to here. So Q in will be equal to H3 minus H2. We have H3 here, we have H2. Now you can see why those properties were important, because here we are going to use them to calculate Q in here. And how about Q out? To find Q out, again, we need to go and see in the cycle. As I said, you need to know the cycle, or the PV diagram for diesel cycle. So Q out is in this cycle from state 4 to state 1. What we have here is the isentropic process, and also we have thermodynamic properties for state 1. So we know the process, and we have the process for one state in this process. First of all, let's see if we can find the thermodynamic properties for state 4 or not. For state 4, we can write this equation because we have a isentropic process. For an isentropic process, we can write this equation. VR4 is equal to V4 divided by V3 times VR3, which is the similar equation which we had for the previous step. Here we have V4 divided by V3, V4 here divided by V3 actually. What is this? If you notice here, V4 and V3, we don't have a direct relationship between these two. But V3, we have equation between we have a relationship between V3 and V2. How? Here we have V3, here we have V2. This is nothing but the cutoff ratio, which we know how much is the cutoff ratio. It is equal to 2. So here, instead of V3, we can write 2V2. So here V4 divided by 2V2 time VR3 will give us the VR4. We have VR3 actually, but we don't have again V4 and V2. But if we again go to this graph, V4 divided by V2, what is it? V 4 is actually equal to V1 because here we have a constant volume process. So V4 or even V1, they are same, divided by V2 actually is the compression ratio. So here V4 divided by V2 is equal to compression ratio, or R. So this equation will be changed to this one. R divided by 2 times VR3. R is given, it is 16, divided by 2 times VR3. VR3 from the previous step. Finally, we can have VR4, which is equal to 36.37. Again, with the same procedure, here again we have found VR4 as a dimensionless property. Then we can use this. We need to go to table A17, use interpolation, and find thermodynamic properties like U4, U, or internal energy for this state, and so on. Here we just need to know the internal energy, or U4, for this state, which U4 will be equal to 659.7 kilojoule per kilogram. Why U? Because in process from state 4 to 1, as I said, we are going to calculate thermal efficiency for the cycle. We need to have Q out and Q in. We have calculated Q in already. How about Q out? Again, let's see where is Q out. Q out is in this process from state 4 to state 1. It is an isentropic process. It is a constant volume process actually, not the isentropic. It is constant volume process. Then we can write write this equation for that. When we have a constant volume process, the change in the energy of the system will cause only change in the internal energy of the system. Q out will be equal to U4 minus U1. We have U4 here. We have U1. We have already calculated, found in previous steps. Then we can finally find or calculate Q out here. And the rest is easy. thermal efficiency will be equal to 1 minus Q out divided by Q in. 1 minus, we have Q out, we have Q in, then we can calculate thermal efficiency for this diesel cycle, which is equal to 56.3%. So we found the answer for part B. Let's see how we can and find the answer for part C of the question. Part C of the question is about mean effective pressure for this diesel cycle. If you remember, we had this equation W net out, or the work, the total output work of the cycle divided by the change in the volume during that cycle, or actually the maximum minus minimum volume of the cylinder during that cycle actually. So here, to calculate mean effective pressure, we need to find W net out, we need to find V1 and V1 minus V2 actually. Let's see how we can find it. First of all, to calculate W net, we have this equation. W net for the diesel cycle which we have here actually, or for heat engine generally, is equal to Q in minus Q out. Q in is given to the cycle, and W net out is the output of the cycle, and Q out is the amount of the energy which is rejected to the surrounding. You know this equation from thermodynamics. So we have Q in, we have Q out, substitute here, and finally we can calculate W net out, or net work output of the cycle, which is equal to 574.07 kilojoule per kilogram. Now, how we can, we have W net out, how we can find this V1 minus V2? We have some relationship between V or the volume in different states actually in the cycle, but we don't have the exact value for the V. How we can find that? First of all, what we have here actually is an ideal gas, so it follows ideal gas law. So we can write this equation: V1 is equal to R times T1 divided by P1. So we can write this equation for all of the states, but because now we have all of the information here, we have temperature and pressure for different states in the cycle. But here, what is easier actually is the information which is given in the question instruction. The temperature and pressure for the initial state, for state 1 actually is given. So we have temperature, we have pressure, and R, as I said, it is a property of the working fluid or the air here, is equal to 0.287 kilopascal meter cube per kilogram Kelvin. So we have R, we have T, we have P. Then we can calculate here actually a specific volume. And do not forget T here should be Kelvin. And you need to check also unit. And finally, a specific volume which we can calculate by this equation is equal to 0.906 meter cube per kilogram. So what we can calculate by this equation, or we have calculated actually, is a specific volume for state 1. And if you notice, for a specific volume, if you remember, a specific volume for any state is equal to volume in that state divided by the mass in that state. Here we have a closed system. M is constant, but the volume in different state in the cycle will change. So we will change. So V1 will be equal to capital V1 divided by M. M is constant. So to actually here, if we have M, we can calculate the volume and then use the equation to find MEP. However, if you remember, this equation is also valid. This W net, the lower W actually is valid for the specific volume. So what we have here is a specific volume, and what we have here also is the work, you know, uh, by work by in terms of unit base actually. Uh, the work which we have here is a mass unit base actually. So W net out, which we have calculated here, you can see is based on kilojoule per kilogram. So here we can put a specific volume. And if you remember this V1 minus V2, if we bring out V1 from this equation, V1 minus V2 is equal to V1. Here V1 divided by V1 minus V2 divided by V1, which will be equal to just simple thing. I'm just going to show you this simplicity actually. V2 divided by V1. If you look at the cycle, V2 divided by V1, it means minimum volume divided by maximum volume, which is 1 divided by R. R is the compression ratio, or V1 divided by V2 actually. So we can write like this: V1 times 1 minus 1 divided by R. So here we have already calculated V1. So we can write V1 here. We have R is 16. Then we can calculate mean effective pressure. Again, you need to be careful about units. Here we have kilojoule per kilogram. Here we have meter cube per kilogram. So we need to use this unity conversion ratio to have MEP, or mean effective pressure, based on the kilopascal. Mean effective pressure is 675.9 kilopascal. So by this, actually we have already finished the answer for this question. We found the maximum temperature in the cycle, the thermal efficiency of the cycle, and also we found the MEP, or mean effective pressure, in this uh, air standard diesel cycle. Next, we will have an example for the Brayton cycle.